Hello everyone. So in the previous class we had discussed the Cauchy's formula, and we had discussed a few important things associated with with the various stress components. Now today we are going to discuss something very important. We are not going to prove it formally, but we're just going to mention it. So all this while we have been dealing with the balance of linear momentum. So what happens if we use the balance of angular momentum? So if we do the balance of angular momentum, for the special case where there are no body couples, so consider when no body couples are present. So just like you can have body forces, you can also have a distribution of body couples in certain special applications, but we will be solely concerned with those applications where there are no body couples. So in this very special scenario, but very common, like it is the exception that body couples would exist. Okay, so it is the far more common engineering scenario that you will have no existence of body couples, and in that case if you carry out the balance of angular momentum, and we are not going to carry out the steps like we had done in the case of the balance of linear momentum. So if we carry forward all those steps, what we are going to get is this conclusion, that the stress tensor is going to come out to be symmetric. So this is the conclusion that we obtain from the balance of angular momentum. It seems a little bit weird that we are dealing with the balance of angular momentum and how come this arises, but you can actually go forward with the entire steps, but in the interest of time we'll not do that. So this is the important conclusion that we want to have, and this is very important. Like, you need to remember this all throughout, that the stress tensor is symmetric. Basically what this means is that sigma 1 2 is equal to sigma 2 1, sigma 2 3 is equal to sigma 3 2, and sigma 1 3 is equal to sigma 3 1. Okay, I believe most of you are already familiar with this in the form that you came across in your first year mechanics, where you said that tau xy is equal to tau yx, tau yz is equal to tau zy, and tau xz is equal to tau zx. So in the same way that you were using for the shear stresses the taus, the Greek symbol tau, we are no longer using that Greek symbol tau. We are just keeping all the stress components to be denoted by the same Greek symbol sigma. It is the index, the subscript present, which will indicate whether it is the normal component or the shear component. And we are going to discuss the normal and the shear components of stresses in a subsequent lecture in a far more elaborate fashion, but for now we just mention it in passing. Now what happens if we actually utilize this new conclusion that the stress tensor is symmetric? So if we go back to the previous slide, we'll see that we had this relation. This is the famous Cauchy's formula or relation or stress theorem, and it is in this particular form written in the vector or compact notation. So if we use this, what we obtain is simply that the relation is absolutely equivalent to this. Please note that time and again I am writing this sigma in the compact notation with a double tilde beneath it. The double tilde beneath it is just a mathematical way of representing that this is a tensor of order 2. So you may say that if that is so, then shouldn't a vector be represented by a single tilde? And that is very much true. There are many people who do represent the vector not by this kind of a half arrow on top of the letter, instead by a single tilde at the bottom. But that is more common among mathematicians. As engineers, it is far more common for us to write the vector with a half arrow symbol, and we'll stick to that convention. Okay, now what is the use of all of these things? It is good to know that the Cauchy's formula can be written in this alternative fashion, exploiting the symmetry of the stress tensor. But what if we want to utilize this back in the equation or the balance of linear momentum? So let us go back and take a look once more at that equation. So we had this nice form for the balance of linear momentum. Now what we want to do is we want to substitute the form that we just obtained for the traction vector, that is this vector, in terms of the stress components, that is the sigma dot n, and we want to proceed from there. So what is the motivation? Why do we want to do this? So it should not be like an arbitrary set of steps that we are doing just because we can. There should be a certain proper motivation for doing certain things. So the motivation is like this. You see, on the left hand side, what we have here is basically a volume integral. Okay, so this is a volume integral on the left hand side, and this is a surface integral. Now this entire equation is in the form of an in the form of integrations. But suppose and very importantly, the physical meaning of that is this equation, this balance of linear momentum equation as written here, it can only be applied to an overall volume. Okay, you have to apply this entire this equation to a total volume. But suppose we want to write this equation locally, that will be applicable at a single point. What then? How can we obtain an equation from this volume integral fashion or the integral fashion to a single point? So that is referred to as the local equation. How can we obtain such a local equation? Well, the first step towards that end is to actually substitute this traction vector in terms of the sigma dot n. Okay, so and you will see in a moment why that motivation is there. Okay, so we are proceeding with the motivation of going from the integral form of the balance of linear momentum. So what we say here is that, getting back to the balance of linear momentum equation, what we have here is the volume integral rho dv dt minus the body force per unit mass dv, and on the right hand side we have the surface integral of the traction vector. Now we are going to substitute this thing here. So we are going to substitute this. We have substituted this sigma dot n here. Now you see, this is a surface integral, and our motivation is to go from a integral form to a local form. Now suppose you think that in some way, okay, this is our wish, that we want to go from the integral form to the local form. Suppose instead of this being a surface integral, suppose if this were a volume integral, then what could we have done? We could have taken this term also common here. I repeat, suppose by some magic this were a volume integral instead of a surface integral, then we could have easily transposed this to the left hand side, and we could have taken everything common under this one volume integral, and then by arguing that since this is a general balance equation and it must be true for any arbitrary volume, the only way that this thing is going to be equal to 0, because you understand that when I transpose this to the left hand side, it will be left with a 0 on the right hand side. So the only way that this entire volume integral is equal to 0 would be possible if the integrand is equal to 0, and that's how we would extract a local form. But that is only a wish. We do not actually have a volume integral here, we only have a surface integral. But by writing this traction vector in terms of this sigma dot n, we are one step towards moving to a volume integral. And how is that? Well, I'm sure you must have a lot of you must have figured out that we can go from this particular form of the surface integral to a volume integral using the Gauss divergence theorem. So what we can do is rho dv dt minus b. So the left hand side remains as it is, and on the right hand side what we'll have is from this surface integral, so this sigma dot n form, if we use the Gauss divergence theorem, we'll obtain the divergence of the sigma, and that will be the volume integral. So here we are using so let me write it below, using the Gauss divergence theorem. Okay, so the moment we have this particular equation, we can go we can transpose this, what we were saying earlier, that suppose we had this volume integral by some magic. So the magic is that we are using the Gauss divergence theorem along with the Cauchy's formula, and from here we can simply transpose it to the left hand side and write this as minus delta dot stress tensor integration over this entire thing dv is equal to 0. Okay, so let me go to the next slide and continue. So I'll write the integration once again. Rho dv dt minus b. I'm just repeating whatever I wrote just now. dv is equal to 0. Okay, so the argument that we invoke in order to go from this volume integral form to the local form is that so because this must be true, when I say this, it basically means this balance form. This balance form must be true for any arbitrary volume we must have the integrand itself to be 0. Okay, so overall this is more commonly written in this particular form. Rho dv dt is equal to delta dot sigma. We just transpose the terms, the two terms to the right hand side like this. So this is the more common form, and this particular form this is referred to as the very famous Cauchy's equation of motion. This is extremely important. Okay, uh, I believe that even in fluid mechanics you came across this equation. Okay, and please note that till now we really have not said anything which is specific to solid mechanics. Like what the steps that we have carried out is perfectly true for any general continuum mechanics uh, scenario, whether it is fluid mechanics or solid mechanics. Later on, as we keep on developing our theory and our framework, we'll see how it can be specialized to the study of solid mechanics. But for now, this is absolutely true for any general continuum mechanics scenario. However, uh, for the purpose of our mechanics of solids course, what is more common to use is not this Cauchy's equation of motion, rather a certain specialized version of it, uh, where we say that for static equilibrium, we do not have any acceleration term. You understand that the time derivative here of the velocity is nothing but the acceleration. So for static equilibrium, this term rho dv dt, that is equal to 0, and therefore what we'll have is delta dot sigma plus rho b is equal to 0. And what that basically means in component form is, maybe I should use the next slide for this. Uh, so what this equation basically means, this particular equation in component form is that so this is the first component. Uh, so if some of you are having some doubt regarding what components I'm writing here, you please note this equation and you try to understand what is the tensorial order of this. If you're finding some difficulty with this term, you can work it out in a slightly indirect fashion by noting that whatever the order here must be, it must be consistent with the order of the other term, because in a particular equation all the different terms must be of the same tensorial order. Now this particular term is very easy to understand. It is just a scalar multiplied by a vector. So this is a vector quantity. More mathematically speaking, it is a tensor of order 1. So no matter what the actual form of this may be, it must be a tensor of order 1 also. So overall it must also be a vector. And just like this vector quantity has 3 components, this one will also have 3 components. And what we are writing here is basically, so these 3 terms together, that is the first component of this vector, and the rho b1, you understand, is the first component of this vector. That is all there is to it. So now we are going to write the second component. So these three terms are the second component of this vector quantity. Again, these three terms are the third component of this vector quantity, and this is of course the third component of the rho b vector. Now you note that in writing these equations, I have actually utilized the fact that sigma 1 2 is equal to sigma 2 1. The sigma 1 2 that is written here, it is perfectly alright, but here I should have actually written, very strictly speaking, sigma 2 1. But I am utilizing the fact that sigma 2 1 is equal to sigma 1 2. Similarly, here this is perfectly alright, but this one, the sigma 2 3, that should actually have been sigma 3 2, very strictly speaking, but again I am utilizing the fact that sigma 2 3 is equal to sigma 3 2, and similarly for this term also, sigma 1, this should be sigma 3 1 strictly speaking, but I am utilizing sigma 3 1 is equal to sigma 1 3. Okay, now these equations, so either this equation in vectorial form or these three equations together, they are referred to together they are referred to as the stress equilibrium equations. Okay, so either this vectorial form or these three equations together, they are referred to as the stress equilibrium equations. And time and again, all throughout this mechanics of solids course, you will have the necessity of actually applying these equations, even in your problem sheets and also in your later chapters. All right. So in the subsequent classes, we'll continue our discussions of the stress components. But for now, we'll stop here. Thank you very much.